Alright, good day guys, how are you doing? We're talking about some things under Kirchhoff's Law tonight. And when you talk about Kirchhoff's Law, it's actually being developed by a particular physicist scientist, which is Gustav Robert Kirchhoff. So his experiment was mainly based on electricity and some other stuff like that. Now, what does actually Kirchhoff does with? It's also the normal thing of you applying under your normal direct current. Let's say direct current, what you do with your EMF, your battery and stuff like that. So the theoretical aspect of some little things there, I'm still going to develop them and drop them on my YouTube channel. But let's move on to something important. Is that there are some certain questions where you are going to be given, and in a circuit they'll tell you, okay, you find the particular total resistance of a particular circuit. You might quickly find it, but it might be much more easier for you if the circuit structure is much more easier. When it comes to a complex them whereby EMF is being utilized and different pattern of current is flowing in, flowing out, it might be much more confused for you to just apply only the series and parallel connection to it, because it might not even be able to handle the situation. So that was what Kirchhoff comes in. That is when it comes into play. Now the Kirchhoff's first rule tells us that this first rule is talking about current. It's talking about current. And what does it say is that it applies to charges that is entering or leaving a junction. What do they call junction? Yoruba we call it, they say, orita meta as a junction. So this is a junction here, a point whereby the current hits themselves, meets their self, or actually a point whereby the point what leaves, enters or leaves. Now it tells us that it applies to charges that are entering and leaving the junction. This is a junction, we can call it junction or we say node. Now a junction is a connection, connection of three or more what? Wires. You're having a particular RB connected like this. In this point, the current, we know already that current is the flow of charge. So what does it say is that the rule tells us that the charge being conserved. What does conserve means? You're not dealing with any particular net flow or maybe a net loss of current or anything. We are only concerned about the current moving in and going out. You're not concerned maybe it's going to one direction or it's not just coming in and moving out of it. Now, what does it tell us is that whatever must flow into that junction in terms of the current must also flow out. That is, the total amount of current that must flow into this junction must also be equals to the total amount of current that will flow out of this junction. That is, if you look at current 1 moving into the junction, current 2 into the junction, current 4 into the junction, and current 5 into the junction, current 6 and current 3 are both moving out. So at that point now, we know that the summation of the total current that is coming in will be equals to the summation of the total current that is going out. That is, I1 plus I2 plus I4 plus I5 will be equals to I3 plus I6. That is what the first law, or let's say the first rule, actually talks about. So this is, we call it literally at times a current rule. Alright, talking about the Kirchhoff second rule. Now this Kirchhoff second rule talks about potential difference, literally we say voltage. How you get what I'm saying? And the difference between the rule 1 and rule 2, I said rule 1 talks about the current law, right? And at times they usually give it this name. They will say KCL and KVL. So this stands for Kirchhoff's current law and Kirchhoff's voltage law. Are you with me? So they do put that kind of thing there also, just like an abbreviation. Now in that time, in that point rather, we've talked about the current law. The second law tells us that in a closed loop, current deals with node or junction, while potential difference voltage talks about the loop. So it says in a closed loop, if an energy is supplied by a particular EMF, a particular EMF might be much more like we say in a battery, let's put it that way, that supplies current to a particular circuit. Let us put it basically that way, in a way you understand. So EMF are debris under your normal talking about your electric current. They should have defined that for you, and you should have understand what they call EMF. Now you see the energy will be broken down into other form, and by the device in that loop. Now if you look at now, when a particular current from the source is being passed into the particular circuit, you should know that there are the voltage at which the particular current moves with. There are different things, or let me just say, in life, this thing is just like in life. In life now, let's assume you want to be successful, you should know you will go through different challenges, right? And each challenges you move or you pass through, it rolls the energy down in order for you to move more. It is only those that have a high them that keep striving hard. Are you get what I'm saying? Now let us now assume that you have a particular money finish, you've strived hard and you've got money. You should know that in that point now, you becoming rich, only you won't spend the money, family will collect, this one will collect, that one will collect. That is just how the same thing it's this particular EMF is. Whenever a particular battery is working in a car, in no time you would see that what the battery will get weaker. That is what, like, a basic explanation of what this thing is talking about. Now it says that the energy will be breaking down into simpler form. That is, it will be transmitting to each particular different thing that is being imposed on that device. You get what I'm saying? So since there is no any way, it's a loop, it is a closed loop. Since there is no way energy can move out or come into the particular circuit, that means that the loop law tells us that if you add all the particular potential difference, including the EMF, the resistor elements, and the rest, if you add them together, everything in that loop must be equals to 0. That's addition of everything. Now we'll break it down in the next chart. Now we are going to break some things down. Now if you look at this closed loop, this is like a simple closed loop. It does not have junction, no junction here, no junction at all. This is also a normal closed loop. It has the EMF, the external, which is the resistor, and we all know the law that it says that the sum of the potential difference will be 0. So we want to confirm by giving you the expression of the formula and also using an example to break the certainty of what we are talking about. So let's look at the breaking down. Now, when looking at the important thing we need to understand, because we are talking about that, we're talking that all the particular resistive elements and the current moving traits, all of them, when you subtract everything from, when you add all of them together with both the EMF itself, it will be equal to 0. Now, from what we want to talk about first and foremost, we actually give the loop designated value. Now, at times, they usually do some certain things like this. You have something like this, at times showing at which the process at which the particular current is moving. The voltage is actually, let's just say the voltage moves, you get, in the aspect or the direction at which the voltage move. So if you look at this kind of position now, you have from A straight to B, straight to C, straight to D, then back to A. So at times, that's why we call it a loop, A, B, C, D, A. Are you with me? So in that point now, we said the loop is A, B, C, D, A. Why? Some people like, why is A being repeated 2 times? It's simply because the voltage will move from A to B, B to C, C to D, then D back to what? A. So that is why we call it loop A, B, C, D. And it's actually much more easier to label your particular circuit in some cases, so as to understand the way it works. Now, if you look at from the positive terminal, now the current will move from A to B. Why? Under normal conservation of the normal law of electricity, or we say current. We say current moves from the high potential, that's the terminal with the high potential, to the what? To the low potential. But in a normal physicist scientist, we all know that literally, indirectly, the current is moving from the negative aspect. But we are not talking about that now. There are some processes at which those are actually being taken under direct current. So what we are actually concerned about is that the current move from the positive region. That's what we are concerned about today. So since it's moving from the positive region, that means from A straight to B. And I told you guys something the other time that if the voltage move past or move across this, the current is also moving with respect to the resistor. Now, at that point, do not forget, from Ohm's law tells us that the voltage varies directly as the what? As the current. Given that what? There's a given that the temperature remains constant. So in that point, we know V varies directly as the current, where you have V equals to what? I R. So EMF is just like the whole source of the energy itself. Like why the voltage we are dealing with, EMF is also categorized as voltage, but we are using voltage like a point where each different category are being breaking down into. Now if you look at this now, it says that from the positive terminal, like we said, from A to B, the potential difference will drop. Now what does it mean is that if the voltage passes through this point here, are you with me? It will remove its own from this full voltage here. That was why, if you remember from resistor connected in series, they will tell you that resistor connected in series have different what? Have different voltage. I'm just trying to give you some little hint. If resistor they are connected in series, something like this. Let's say resistor 1, resistor 2, resistor 3. The voltage that will pass through this resistor will be different because they are connected in series, but they have the same current flowing to them. Do not forget. So at this point now, we could give that same them, that is, we have the same current flowing through this loop, but because it is a closed loop, but the voltage would be different for each work that it's actually utilized. That means that if the voltage, if the EMF, the source itself, passes through resistor 1 here, resistor 1 will move. It's just like Nigeria money. Anybody that gets to there, they just take their own share. This one take his own share. That means that if you want to note or you want to get the remaining EMF that will be moving through all this one, you have to subtract what? The one that is being what? Being depreciated from the total EMF. Are you getting what I'm saying? The same thing again. When it moves through this point, this one will also take his own. Are you with me? So this point over it gets to here. When it gets to here, this one would also be subtracted from, this one has removed its own. This one also remove its own here. Then when it moves from C to D, at the point at which it moves from C to D, the voltage will also be utilized. Are you getting what I'm saying? So, but if it moves from D to A here, nothing will happen because there is no any component here. So at this point at which we are discussing, we said from B to C, the potential difference will drop again across R2. C to D, it will drop again across R3. D to A, nothing will happen because there are no components. So the source of EMF of that voltage, which is the 12 voltage, and the resistive element, when you add all of them together, it must be equal to 0. So breaking down the second part of the chart, let's go to the third part of what they are trying to explain to us much more. So what are we talking about? We said the summation of the EMF, which is the source, plus all the particular resistive elements with respect to how they are being breaking down will be equals to 0. That is the potential difference law. Now if you look at now, like I said now, this is a resistance with a current moving through it also. The voltage comes in. Now this one we can call this voltage 1 moving through this. And voltage 1 would be equals to what? Current times what? Resistor 1. Don't forget. This one will take its own share from here. So it's just like you saying the EMF minus voltage 1. Are you getting what I'm saying? And the remaining now would be the one that will feed this part. This one, so now we have another voltage 2, which is equals to, we say IR2, because this one too will take its own from the EMF full source. So at this point also now, the same thing will occur. You have a voltage 3, which is equals to IR3, because this will also remove its own. So at that point now, that means that the EMF now would be subtracted from voltage 1, because we want to know the remaining one that moves through here. We also subtract it again now from voltage 2 to get the remaining one that will move through here. We also subtract it from voltage 3 to get the remaining one that will move through here. Are you getting what I'm saying? So they told us that the addition of all this, so the voltage, which is the EMF, at that point, the addition of the EMF plus, we know that it can't be plus, because plus minus you still have minus. So plus, let's just put it that way, plus the voltage 1 plus the voltage 2 plus the voltage 3 will be equals to 0. And what is under voltage 1? IR1. Voltage 2, IR2. Voltage 3, IR3. That is the 3 voltage we have that utilize all the EMF. I will be equals to 0. So if you look at now, at this point, this kind of breaking down, this kind of simple loop, we can get our current from here if you have been asked to find current. How? We know that what is resistor 1? Resistor 1 is equals to 1 ohms. Resistor 2 is equals to 2 ohms. Resistor 3 is equals to 3 ohms. Right? And at that particular point, if you have to look at it, if you have to break this down, we know this is summation. Summation means the addition of all the particular trash that we have there. Now we know that the EMF, which is the full voltage, is equals to what? 12 volts. And at that point, we know that you can say V negative IR1 minus negative IR2 minus negative IR3 will be equals to 0. Right? And at that point, you can say V negative I into brackets R1 plus R2 plus R3, because negative I is common to both of them, do not forget, equals to 0. So at that point now, we know our V, right? So you can say um, negative I into brackets R1 plus R2 plus R3 can be equal to, if V comes here, you have negative V, right? So at that point, negative, we cancel out negative. We have the current into brackets. What is R1 to R3? You have 1 plus 2 plus 3 equals to what? 12. So therefore now you have I times what? 1 plus 2 you have 3, 3 plus 3, 3 plus 3 you have 6. That's you saying I times 6. That's 6. I equals to what? 12. Divide both sides by 6 over 6. That means your current that is flowing through them will be equals to what? 2 ampere. So are you get what I'm saying? So this is like how we utilize the Kirchhoff's law in order to find current, more than one current, and multiple voltage and stuff like that. Are you get what I'm saying? But this is like the basic aspect to explain and expatiate some little things you need to understand as someone who is new to Kirchhoff's law. So please like and subscribe for the part 2.